We are doing Chapter 3, Section 8, Implicit Differentiation. So what is implicit differentiation? I'll explain this to you. So in the past, when you're taking derivatives, you always had the form y equals some function. And you just took the derivative directly. But if you look at this, you don't have y equals. So how do you take the derivative if you don't have y equals? And so that's what implicit differentiation allows you to do, is when you don't have a function set up as y equals. Now, in fact, this equation, you should know it's a circle, and it's not even a function, because you should remember to be a function for every x value, there can only be one y value. But if you draw a vertical line, this x value contains two y values, not a function. This x value here contains two y values, not a function. So you couldn't even write this as y equals as one function, and you'll see what I mean by that. So implicit, it's non-direct differentiation. Explicit is what you've been doing so far this year. So what we're going to do is I'm going to subtract x squared from both sides, and that'll get us y squared equals 4 minus x squared. Then I'm going to square root both sides, but remember we have to put a plus or minus in front if we do that. So we get y equals plus or minus square root of 4 minus x squared, which I have written there. But what does that really mean? That means I have two functions, 4 minus x squared and the opposite of 4 minus x squared. So what does this actually tell us? Well, this first part right here, you should notice that square root's always positive. So when you graph that, you only get the top half of this graph. It's never negative. So it's always positive. You only get half of the circle. That is actually a function because for each x value, there's only one y value. It doesn't cross anywhere twice. And then we have the second function here. And you'll notice you'll get the same value when you plug in x, except after you make it negative. So positive 2 will end up being negative 2 because you take the opposite. Positive 1 will end up being negative 1. Positive a half will be negative a half. So you see all the values on top get reflected to the bottom. You should remember that from pre-cal. When you have a minus in front, it reflects over the x-axis. So this graph will give you the bottom half. And that's what's happening. So you would have to have two separate functions if you wanted to take the derivative directly and then take the derivatives of those individually. And depending if you're on the top half or the bottom half, you would have two different derivative equations. So that's what's happening with that equation. We're going to do implicit differentiation. How do you take the derivative of this without separating it out to two separate functions? So here's my example. Calculate dy dx directly from the equation for the circle x squared plus y squared equals 4. The first thing I want to remind you, y equals plus or minus the square root of 4 minus x squared. So that's, if we were to solve for y, it would look like that. But more importantly, you have to see that y is actually a function. Y equals this function. And another hint, I keep reminding you, that top number tells you what your function is. The bottom number tells you what your variable is. So you need to look for those x's to take the derivative, and that's normal. And you know the derivative of that is just 2x. So we could just take the derivative. But here's where it gets tricky. Y squared, y is not your variable. Y is your function. Y is some function if you solve for y. So that's kind of crazy. So what do? Well, this is chain rule. Last chapter, when you had a function inside of another function, you use chain rule. So that's what we're going to do here. Now, we will call y our box. because that's the function that's on the inside. So what did we do when we did the chain rule? Well, we treated box as a single variable, but it's actually a function. So the derivative of box squared would have been 2 box to the first times the derivative of box. So I'll write it that way. It's 2 box to the first. I usually do box in red. So it's 2 box to the first times the derivative of box. Well, what's box? Box is y. And the derivative of box. Now, this one is so easy it might confuse you. What's the derivative of y? Well, by definition, it is dy dx, right? So don't be confused when I put dy dx. That is the derivative of y by definition. That's pretty easy. And then the derivative of a constant on the right side is 0. So what do we have? 2x plus 2y dy dx equals 0. And what is our goal? We want to know what dy dx is. So we're going to isolate this. We need to get rid of those two using basic algebra 1. So we will now subtract 2x from both sides to get rid of that. Those cancel. We get 2y dy dx equals negative 2x. Now we will divide both sides by 2y to get rid of that. And those 2's cancel, and we have our derivative of y with respect to x. It's going to be the opposite of x over y. We have found the derivative of y with respect to x using implicit differentiation, because it wasn't an equation where we had y equals. If we would have taken the derivative of that, that's explicitly. This is not directly, it's indirectly, it's implicitly. Now part B, we should know that the derivative tells us the slope of the tangent line. What's interesting here, which is different, in the previous derivatives, you never had y's in your derivative. It was only x. So to find the slope, we only plugged in an x. But in order to find the slope in this case, we need to know the y coordinate. And this should be significant also. Let me show you the notation that you've seen, but probably hasn't sunk in, and it needs to. It's going to be this notation. This means the derivative of y with respect to x at the point where xy equals 1 radical 3. So that point, 1 radical 3, is right there. So we want to find the slope of the tangent line at that point. Well, how do we do that? We take our equation here, and we replace x with the 1 and y with the radical 3. So we get negative 1 over radical 3. There's our answer. Now you can leave it like that. If you want to rationalize it, you would get that. Either form is fine. But that is the slope at that point. Negative 1 over radical 3. And that makes sense. Look at the slope of this line. Isn't it not negative? So the tangent line has a negative slope. Now, you have to realize at the point 1, there's another point down there. That's where your y value is negative radical 3. So if we want the slope of the tangent line at that point, we would have to use negative radical 3 for the y. So then we say, hey, what's the derivative at the point where xy equals 1 negative radical 3? Well, we just do the same thing. Plug in 1 for the x up top. Plug in negative radical 3 for the y on the bottom, and it comes out to be a positive 1 over radical 3. And that should make you happy because that's a positive slope. Positive answer. Negative slope. Negative slope. Everything matches up. So that's our first example of taking derivatives implicitly. We're going to do quite a few more. And my recommendation is to pause, so I'll show you the question, and try to do this one before I do it. So here's the hint. You have a chain rule going on already. I'll give you a heads up. So you have a situation where you have sine of box. When you take the derivative of box, you have to do product rule on the inside. So that might be a little weird for you, but go ahead and try it. Now, what you can do if you get stuck, you can play my video, and when you get to the part that made you stuck, pause again and see if you can finish this. And we're just going to do a bunch of examples the rest of the way. Okay? So here we go. I have sine of box, just like the chain rule in the last chapter. So what is the derivative of sine of box? That's going to be cosine of box times the derivative of box, and that's going to take some space, so I gave myself some room. On the right side, 2x, remember, y is your function. X is your variable. Whenever there's an x, you just take the derivative normally like you always have. So you bring the 2 in front and decrease the power by 1. And, okay, don't make this harder than it is. What's the derivative of y? Now, y is a function, not your variable, but by definition, the derivative of y is dy dx, right? So don't make that trickier than it actually is. That's by definition. So box is xy, back here again. So derivative of sine box, it's cosine box. Remember, that stays the same. Don't take the derivative and put it here. That's the big mistake people make. Now the derivative of box, I need the derivative of that, but that's a product rule. So I leave the first alone and take the derivative of the second. Well, again, what's the derivative of that? By definition, derivative of y is dy dx. Plus, the derivative of the first one is just 1, leave the second alone. So let me rewrite that. This is where your algebra skills need to take over. Okay, you want to isolate dy dx. What does that mean? Anything with the dy dx you want on one side, anything without you want on the other side, because that's what you're trying to isolate. Now, a little note that I didn't mention, but on this problem, you couldn't really solve for y. If you wanted to take the derivative explicitly and get a y equals function, good luck on that. Yeah, that's going to be not very fun. Okay, so how do I get all the dy's, dx's on one side? I have a problem here. That thing there is stuck inside these parentheses. So that y that doesn't have dy dx, it's stuck. I can't get rid of it. I can't move it to the other side. I have to set this dy dx free of the parentheses, and that's going to happen only if I distribute that. So through practice, hopefully you start seeing that. So I'm going to distribute these two. I'm going to get x. I'm just rearranging because it looks better with the x in front. Dy dx. Then I distribute these, and that's just y cos xy. And the other side is just fine and dandy. So here's the thing. This doesn't have an dy dx, so I'm going to subtract that from both sides. And then this, I want the dy dx is on the same side, so I'm going to get rid of it here by subtracting that. I'm going to do that all in one step. You know what? And I need some room. I'm going to slide this over to the left so I have some room. So what I'm going to do, I don't want this, so I'm going to subtract it from both sides. Whoa. And then I want to get all the dy dx's to the left, so I want to get rid of this dy dx. So I'm going to have a minus dy dx. Those will cancel, and these will cancel. And here's what I'm going to have left. I'm going to rearrange the left side again. I'll explain what just happened there. And then on this side, I have 2x minus y cos xy. So I'm subtracting dy dx, but I like the negative to be in back, so I just switch these. I put this in front, and then you're subtracting dy dx, so I just did that. Okay, I still don't have dy dx by itself, so I need to factor out the dy dx, because you'll notice both terms, there's two terms. Terms are things that are being added. There's two terms, and they both have a dy dx. So I'm going to take the dy dx out in front. And what's left over? Well, if I take that out, I'm left with x cos xy. And if I factor the dy dx out, I'm going to be left with a minus 1. And remember, you're doing backwards factoring. You're not going to have nothing there, because when you distribute that, you need to end up with that. If you put a 0 there, it wouldn't match up. So we have that. On the right side, everything stays. Now, how do I get rid of all of that? Well, if something's being multiplied, I divide by that. I will divide both sides by x cos xy minus 1. X cos of xy minus 1. Those will cancel, and I have my final answer. dy dx equals 2x minus y cos xy over x cos xy minus 1. Whew, yeah. I know that's a lot of work, but if you go over this, is basic algebra with weird terms, weird things. That's that example. Let's just keep going. We're going to do a bunch of examples. And I'm going to show you some secrets that might make your life easier. The equation of the tangent line. Oh, I know the equation of a line. I learned that. I've been quizzed on that many times. How nice of them. They already gave me my x1, y1. They told me the exact point of tangency. So I have those two. All I need is the slope. I wonder how I find the slope. By definition, the slope of the tangent line is the derivative. So we need to find the derivative, which is dy dx. Now, this is another case. Can you solve and get y by itself? You might, but good luck. It's a lot of work. You can try it for fun and see that it's not so fun. So we are going to do this using implicit differentiation. So we need dy dx. And remember, y is a function, x is our variable. So when you see that, that's box and that's box. When you're doing chain rule, you got to understand any y is a function, treat it as box. So the first part's easy because x is a variable, and so I bring the 2 in front and decrease the power by 1, so it's x to the first, which is just x. Now is the careful part. This is a product. You have to use the product rule. So we let the first alone, and the derivative of y, the derivative of the second, is by definition dy dx. Don't overthink that. Plus the derivative of the first, and you leave the second alone. Here, y is box. What is the derivative of box cubed? Well, it's 3 box squared, right? That's going to be 3. Oh, you know what? I don't want to confuse you guys. That's my product rule. Minus 3 box squared times the derivative of box. But what's the derivative of y? By definition, the derivative of y is dy dx. You learned that early in this chapter. So what's box? Box was y. And on the right side, 7's a constant. The derivative of a constant is 0. Now I'm going to do something here, and then I'm going to erase it and show you another way to do this, an easier way. So we want to solve for dy dx. We want to get rid of anything that doesn't have dy dx. So these parentheses here are not needed because I'm not distributing anything in. So I'm going to rewrite it without those parentheses. Now, I want to isolate all my dy dx's, so I want to subtract the 2x from both sides, and I want to subtract the y from both sides because I only want dy dx's. So I now have x dy dx minus 3y squared dy dx. And this process is going to be very similar on a lot of these problems. Now, we want to isolate dy dx. We have two terms, and both terms have a dy dx. That's the common factor. I'm going to take that out, and I'm left with x minus 3y squared. The last step, I'm going to divide both sides by x minus 3y squared. Those will cancel, and I have now found dy dx is negative 2x minus y over x minus 3y squared. Now we wanted the slope to solve this equation here, right? We had x1, y1, we just need the slope. So I need to find the derivative at 3, 2 to find the slope. So how do I write that? I write it like this, dy dx at the point where xy equals 3, 2, make sure that's right, and I replace the x's with 3 and the y's with 2. Whoops, that's not right. 3 minus 2 over 3 minus 3 times 2 squared. And that's going to be negative 6 minus 2 over 3 minus 12, which is negative 8 over negative 9. 8 over 9. I hope I did the math right. Yeah, I think we're good. 8 over 9. So the final equation, we start plugging everything into this. Our point is 3, 2, so it's y minus 2. Our slope we found is 8/9, and our x1 was given as 3. And there's the equation of our tangent line. Now there's a good chance I made some error and it's not 8/9, but hopefully it is. But I'm going to show you an easier way for a lot of you to do this. An easier way. So let me back up a bit. Where did I get dy dx? Oh, you know what? I'm going to back up all the way to here. Let me erase a bunch of stuff for you. I'm going to erase all of this. And that's not the right tool. Okay, once you've taken the derivative and you get it to this form, you can actually replace your x's and y's at this time. I can place 3 in for all the x's, no more, just those two, and 2 in for my y's, and solve for dy dx. And some of you like this better because you have like nice numbers to work with. So 2 times 3 plus 3 dy dx plus 2 minus 3 times 2 squared dy dx equals 0. And so if you don't need the actual derivative equation, this is easier to do. I recommend highly doing it this way. I'm just going to multiply things out. 12 dy dx. Well, the 6 and 2 will get you 8. And 3 minus 12 gets you minus 9. I subtract 8 from both sides. Divide both sides by negative 9. So, same thing. Much faster, much easier. So if you're given a specific point, I would just plug the points in and not isolate the dy dx until after you plug the points in. All right. Here we're going to find the second derivative. So first we have to find the first derivative, Then we have to find the second derivative. So let's go through this process. You can try this on your own, but there's a little trickiness in finding the second derivative. We've already found the derivative of x squared plus y squared is 4. Very similar. Now it's 1. And you will probably find it comes out the same because when you take the derivative of this, no matter what it is, it comes out 0. But let's do it. So the derivative of x squared, it's 2x because x is our variable, not our function. But y is a function. Y that we're looking at here is our function, so treat it as box. So the derivative of that would be 2 box times the derivative of box. But the derivative of y, by definition, is dy dx. And the right side is 0. Subtract 2x from both sides. Divide both sides by 2y. And you get the same formula we got last time. That is the slope of the tangent line. But we want the second derivative. How are we going to do that? Well, we take the derivative of the derivative. So we take the derivative of that. So here we go. The second derivative of y with respect to x is, now realize this is a quotient rule, low and a high, numerator, denominator. So we have to go low d high, but the derivative of negative x, opposite of x, just negative 1. Low d high minus high, d low, y is a function. Remember, this is box. So the derivative of y, by definition, is dy dx. So that's low d high minus high d low all over low squared. Let me just make this a little prettier. So we're almost done. The only problem we have is this. What is that? But you found that earlier. It's just opposite of x over y. So you just plug that in for your dy dx. So we're going to get this. Okay, again, what did we do? What's dy dx? We found that earlier. It is minus x over y. So I just replace it with the equation, and I put that there. And this is all over y squared. And let's just keep going. So it's going to be minus x squared over y squared. Now that is an acceptable answer, but not a pretty answer. And so this would be fine on an FRQ, but if this were a multiple choice, and that answer might not appear as one of your choices, you have to be comfortable fixing this. We don't like fractions and fractions, so we get rid of it by multiplying by 1. Our 1 is our common denominator, which is y. And I now distribute this. So I distribute these, and I get minus y squared minus x squared. And on the bottom, I get y cubed. So that is a fine answer there. If you want to factor a negative out on top, you can get x squared plus y squared over y cubed like that, which is a little prettier. But however you want to, at this point, it's fine. Just realize the different forms of that answer. All right, let's keep going. What is this? So this is, again, we're going to start incorporating everything that you've learned for the whole chapter. And so if you didn't learn an earlier section, it's going to be very painful. You need a lot of practice. So the slope of the curve. Oh, the slope of the curve, that's the slope of the tangent line. Oh, that's the derivative. So I want to find the derivative. And golly gee, I cannot isolate the y. So when I take the derivative implicitly, you have to treat every y as a function because y is the function, x is the variable. So let's do this. Now this is tricky because you have chain rule. You have 2 box to the 2/3. So This is why chain rule is so important that you see it. It's 2 boxed to 2/3. So the chain rule says you bring the power rule says you bring the 2/3 out in front and subtract 1 from the exponent, right? So the 2 stays in front, the box stays there, you subtract 1, so it's negative 1/3. Then you have to multiply by the derivative of the box. We need the derivative of this inside, and that's actually pretty easy. The derivative of x, that's just 1. And the derivative of y, by definition, since y is a function, the derivative of y is dy dx. And then on the right side, the derivative of y, by definition, is dy dx. All right. Wow. Craziness. Let me rewrite the left side. The negative exponent is no bueno. So we move it to the bottom to make it positive. And how do you get rid of that denominator? Because we don't want a fraction. Multiply both sides by that. Wow, this is going to get pretty weird. Those cancel. And now we have this. Now I'm going to do 2 steps in one. I'm going to distribute that 2 to set that bracket free, or the parenthesis free, however you view it. All right, we are getting somewhere, but we're not quite there. Remember, we want to isolate dy dx. So I want to get everything with a dy dx on one side. So what I'm going to do, I'm going to subtract this to get rid of it from both sides. So those are going to cancel on this side, and I'm left with 2 equals dy dx x plus y to the 1/3 minus 2 dy dx. Again, I'm trying to isolate dy dx, so we have 2 terms, and they both have a dy dx, so I will factor the dy dx out. And what am I left with? X plus y to the 1/3 minus 2. Well, if I want this by itself, I divide by that, and I get this. Let me move that 2 over. That's kind of ugly there. 2 x plus y to the 1/3 minus 2. And there is our derivative for that one. So that's using a lot of rules going on there. A lot of different ones. And you just need a lot of practice. We're almost done with this chapter. We have a test coming up where you're going to have to do these. And so, yeah, I just encourage you, practice this a lot. And I don't even think I'm finished yet. And I think I have an error somewhere. Let me double check this. No, I think we're good. Let me see. Yeah, I think we're looking good so far. Oh, we want a point. Now, I must confess, and you wouldn't even know if I didn't tell you, in the original problem, that was supposed to be a 1, but I left it a 2. So this point actually is not a point on this curve, but you don't know that. And like I said, if I didn't tell you, you may not have known. Someone might notice this, but I'm going to cheat and just use that point anyways. So I want to find dy dx at the point where xy equals 4. So again, you could have, and it would be highly recommended, excuse me, at this point right here. No, I hadn't taken the derivative, had I? I did. At this point here, you could have placed 4 here and 4 here and been done with this and solved for dy dx. Life would have been easier, but it's good to practice both ways. So we're going to get 4 plus 4 to the 1/3 power minus 2. So that's 8. Actually works out well. But the 1/3 power is the cube root of 8, which is 2. Oh, it's undefined. So it has an infinite slope at that point. It's a vertical tangent line at that point. All right. Yeah, if I would have used the correct point, that wouldn't have come out that way, but that's fine. Understand when your derivative is infinity, that's a vertical tangent line. In reality, in this one, that point doesn't even exist. That's probably why it came out that way. All right, is this the last? Oh, we have 2 more examples. You can pause and try this on your own, and I'll just keep going and you just restart and see what happens. So we want the derivative. We want dy dx, and you have to notice this is a quotient. Quotient, you're dividing 2 things. So you have to use the quotient rule there. And remember on top of that, that y is your function. X is your variable. So every y, you need to treat it as box. So the left side's pretty easy. What's the derivative of that side? By definition, dy dx. You learned that very early on. So here we have to do low d high. Low d high is just 1, because derivative that's 1, derivative that's 0, so just 1, minus high d low. The derivative of that's 0, but the derivative of y is dy dx over low squared. All right, this is where it's not going to be fun. We're going to have to isolate dy dx's. So first of all, we don't like that there. So we're going to multiply both sides by that so that we don't have that. Those will cancel. All right, we're going to have y minus 1 squared dy dx equals y minus 1. I distribute that. And then I'm going to distribute that and that. They'll give us minus x dy dx minus dy dx. We are getting close. So both sides, I'm going to add x dy dx, and I'm going to add dy dx to both sides, plus x dy dx plus dy dx. And the dy dx's will be gone from that side. And on the left side, I'm going to have y minus 1 squared dy dx plus x dy dx plus dy dx. On the right side, y minus 1, everything else is gone. I have 3 terms, and they all have a dy dx, so I'm going to factor that common factor out, and I'm left with y minus 1 squared plus x plus 1. And now I will divide both sides by this whole thing, and I get dy dx equals y minus 1 over y minus 1 squared plus x plus 1. That is my final answer for that problem. Okay?